Hi everyone, this is Mr. Cure. This video we're going to be looking at something called vapor pressure. So what we have here is a nice hot cup of tea or coffee. And what's going on here is we have steam or water vapor rising from the surface. Why is that happening? Well, the water or the liquid in here is not quite boiling yet, but we still have this loss of water vapor. So let's explain what's going on. So the idea is we've got all of these water molecules. Remember, they're all in here. They're all attracted to each other with intermolecular forces. So there's quite a strong intermolecular force here with the hydrogen bonds. But remember, these particles are moving. And the higher the temperature, the more these are going to be vibrating and moving around. And at some point, the water molecule might move around so much that it has enough energy to break free of the intermolecular forces holding it to the other water molecules. And as a result, boop, it comes off and it forms a water vapor molecule. So in other words, we have water vapor resulting from the movement of the water molecules and escaping. Now, obviously, the higher the temperature, the more energy these particles are going to have, and the more molecules can enter the vapor phase. So we can actually look this up in a table, and this is the what happens is as you have more water molecules leaving into the air, they exert a pressure as well. Remember, it's a water vapor, so partial pressure. So you can have the pressure of the atmosphere, but you also have the pressure of the water molecules. And the pressure of the water molecules depends on the temperature because the more or the greater the temperature, the more water molecules are going to be in the vapor. And as a result, you're going to have more water molecules hitting the walls and you're going to have a higher pressure. So what you do is you look up the temperature of the water, and then you can look up the associated water vapor pressure that goes with it. So this is the note that we have, and just a quick reminder. So again, what we did the other day is we collected a gas, and we used a pneumatic trough or a water trough. So we bubbled the gas through water, but we're bubbling the gas through water here. We're going to have some of the gas enter up here, but also some of these water molecules. So we have to take that into account. So what you're going to do is you're going to measure the temperature of the water, and then you look up the water vapor pressure over here. And then if you know the pressure of the atmosphere out here, that's going to be the pressure inside here as well. So what you do is you take the overall atmospheric pressure, you subtract the vapor pressure, and that gives you the pressure of the actual gas that you're collecting. So this is what it would look like. So for example, if I had here my atmospheric pressure on my barometer, 102 kPa, and see the temperature of the water was 21 degrees. So what I do is I look up in my table over here, the vapor pressure at 21 degrees. So boom, 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 here it is, 2.49 kPa. That's the pressure just because of the water molecules. Let me go back. So the total pressure, remember the Dalton's law of partial pressures, the total pressure in here is due to the gas plus the water. And together the gas and the water pressure equals 102. So if I know the total pressure from the barometer, 102, if I know the water pressure, I can measure the pressure of just the gas. And this is important because when we're doing calculations, I just want the gas pressure. So here I simply take 2.49, subtract it from 102, giving me 99.5, and that would be the the pressure of the gas. And then I can do some calculations with that. So for example, I can use my ideal gas equation and then use pressure over here from of the gas to make any calculation that I want. And this is the note that you have. So you should copy this down. So again, it's very similar to what we had on the previous slide. So again, the barometer is going to indicate the total pressure in here inside the collection tube, the gas collection tube. And the total pressure is equal to the pressure of the gas plus the pressure of the water vapor. And then what we do, again, we get the temperature of the water. We, from the table, get the water pressure. We're going to know the total pressure from the barometer. You find the difference, and that gives you the pressure of just the gas. And again, you use the ideal gas equation to calculate anything you want. So here's another part of the note down here, and you have your very own table. So let's look at a quick example here. So what I have here, we've got oxygen gas collected over water at a pressure of 97.3 kPa. So this would be the pressure of the barometer, the total, the P total. This is the pressure in the air. The 30 degrees is the temperature of water. So what I do is I look up the pressure of water, the water vapor pressure at 30 degrees. You look it up, it's going to be 4.24 kPa. I know that the total pressure is 97.3. You find the difference, and the pressure just due to the gas is 93.1 kilopascals. Okay, so that's what you typically do. Now let's look at the third example here. So this one here, very similar, you got nitrogen gas. So again, it doesn't matter what you're collecting. So we have the pressure is 98.1. This would be the total pressure. The water vapor pressure, well, the gas is collected at 20 degrees. So what you do is you look up the water vapor pressure in the table. So it'll be 2.34 kPa. You find the difference, and the 95.76 kPa is the partial pressure of nitrogen. And then what you do is you'd use this pressure in the ideal gas equation to calculate whatever value you have to. That's it. So vapor pressure is relatively straightforward, very easy. It's going to be the basis of the lab that we do this particular unit. Take care.